I'm Richard. I'm actually working on the Small Changes Quant and AI Resilience project, the acronym for which is SCQUAIR. I'm not sure if that was a good idea, but it's using Professor Michael Batty's QUANT engine, which is a spatial interaction model. I'll show you how that works in a minute. We've actually finished this project. Our two researchers, Shinny and Alison, these are the ones that have done all the work. So what I'm about to show you is the result of all their work on this project. So QUANT is a spatial interaction model. We've got road, bus and rail in the QUANT model. I've shown cycle here because cycle and active travel was added after the DAFNI project started. So the road, the bus and the rail, these are flows of people. These maps, they all show the people flow much better than anything else does. Each one of the arrows on these maps is an origin zone, and what it shows is the little arrow shows the flow from that origin zone in the average direction that people are commuting from that zone. So you can see it's clustering around big centres of population, big centres of jobs. But the length of the arrow is proportional to the length of the flow. If you just look at the rail and the road, you can see that they're very different spatially, and I'll come back to that later. There are 8,436 zones in this model. Now, it's built from the census question: where do you live, where do you work, what mode of transport do you use to get there? So what we need is a cost function for our spatial interaction model. So for the road, we use the Ordnance Survey data. We use every road in the UK from the OS data. We know the speed limit, and from the speed limit and the length, we can calculate what the transit time for that road is. From that, we can then do all pairs shortest paths on 8,436 zones. So that's 72 million shortest paths on what is an 8.4 million edge network. So QUANT is a computationally intensive model. Now for the bus and ferry network, and for the rail network, we use the timetable. So we've got every bus timetable and every rail timetable for the whole of the UK. And from that, we can gauge the time to transit between one zone and another zone. I've got two maps for the rail here, because one is actually the physical track. That's the one on the left. The one on the right is actually the timetable network, because just because there's track doesn't mean the train is actually going to stop there. So once we built our model, this is what QUANT does. I mean, this is a Heathrow third runway scenario. What we do, we put the numbers of jobs in that is on the government white paper for the Heathrow third runway. We put those in as extra jobs and then modelled it. And so what QUANT tells us is where people are going to want to live in order to get to these new jobs. So the green outlines are showing you where the new jobs are. Now what we've done here, because this is a really bad carbon scenario, because of where the airport is, where the new runway is, everything gets pushed into the centre of London because of where the green belt is. The green belt is actually right on where you see the airport symbol there. So everything's been pushed into London. So everybody's trying to drive to work, basically. So we can plot the differences between the different modes, and we can show how much driving there is as opposed to how much people are using rail. So this is what QUANT does. You put changes to jobs in, or you put additional infrastructure in. So we've put additional infrastructure here to try and mitigate all those new jobs which are going to push people into central London. So the idea is that it models where people are going to want to live in order to get to the new jobs along the infrastructure network. Okay, so the methodology for the SCQUAIR project was, okay, what if we take every one of the 8,436 zones and we build every single link, rail, bus and road scenario that we can build. So essentially we just take the graphic on the left here shows you what we do. You take an origin zone in the middle and you take all the zones that are within 5 kilometres of it, and then you build a new piece of rail link, run the model, see what the impacts are. So we do that for 175,000 different origin zones. So the map on the right here shows you the connectivity of the UK in terms of 5 kilometre links. You can see the pink here is showing you where there's one or more links from an origin zone outside. And you can see it's basically following population density, because these are MSOA zones. So the size of the zone has got to be smaller than 5 kilometres, basically. So what it's following is where the people, where the greatest density of people is. It turns out we have a branching factor of about 20, so on average a zone has about 20 links, apart from those big holes in the middle of the UK. So what we do, we create exhaustively every single link scenario for bus, road and rail, but then we started generating 2 link scenarios. Now the idea about the 2 link scenarios is it does 2 things. So if we put a geographic bounding box around a 2 link scenario, of course we've got an exhaustive set of 1 link scenarios. So the green ones are showing you the 1 link scenarios all around the vicinity, geographic vicinity of the 2 link. So we can run the model, generate the impacts from the 2 link, and then look at combinations of the 1 link to see how good our 2 link scenario is related to any permutation of 2 1 link scenarios. So this is our evidence for the small changes working. The idea being, given that geographic area, what's the maximum benefit you can generate to the population, from that geographic area. It does another thing as well. The idea is that the exhaustive links that we've got, which are the single links, can be used to predict the double links, triple links, quadruple links, and bigger scenarios. So what we're trying to do is to generate from the 1 link scenarios like a base of data that then lets us move up the level. Actually, as I said on the last one, there's 3.5 million 2 link scenarios, and there's only 175,000 1 link scenarios. So computationally, if you're building something like Crossrail, it's computationally very difficult to do every single Crossrail size scenario, or even to explore in the region of a Crossrail size scenario, because your fan out, your branching factor is 20. Now, what it shows us here is that we've got 2 link scenarios and exhaustive 1 link scenarios. The rail, which is the orange column, and the bus, which is the blue column, they actually show that the impacts are actually quite additive. The road, on the other hand, is not behaving in the same way at all. So we can actually predict with quite a good R squared. If you've got a bus or a rail scenario and you start combining links together to make what is a computationally complex scenario, we can actually build it up from predictions of a simpler scenario using the data that we've already run. So while we're talking about predictions, the idea was to use an artificial neural network. We were looking at Gaussian emulator models for another project. The ANN model actually matches this quite well. The short answer to this is, again, we can predict rail and bus quite accurately. Road, not so much. But what this is doing is it's not just predicting from the impacts, this is actually predicting the model outputs. So what we're training is an artificial neural network to predict what a spatial interaction model is going to produce. And the takeaway from this is what we had to do was to put in the size of the network change. And I've talked a lot about impacts and costs and benefits. I'm going to skip over this because there's an awful lot you can say about impacts. I've glossed over it, but we can measure impacts in terms of counts of people, numbers of network changes. We can measure distances, so amount driven on road as opposed to amount on rail. We can use that as a proxy for a low carbon scenario. So if we take kilometres off a road and put it onto rail, we assume that's good for the environment. And then we've got more complex metrics like robustness and resilience. So if I've called it persons per kilometre. So if I put in a kilometre of track, how many people am I expecting to change mode? If I put in a kilometre of track, how many people does that take off of road and put onto rail? And people per second. So if I improve a piece of rail track by, say 30 seconds, how much of a benefit do I expect from that? There's a whole lot I can say about that, but I haven't got the time to say it. So what I wanted to get out of this was a visualization that I could show to an urban planner that says, this is the piece of data that you need. This is the map that you need that shows you how to make high impact scenarios in the UK. Now, this is what I've got from Alison. So this is Alison's work on the geography. So if you look at the map on the left, that's purely the network effects. So I've made one change to the rail network, and it's produced, a certain impact, and then the maximum impacts are plotted for each of the zones in the model. Now, that's not running the quant model. That is literally just a network effect. On the right is the quant model. Now, if you look at those two maps, they're virtually identical. So in other words, the change in the quant model is being driven very strongly by the change in the network. But there's more to it than that, because there are outliers, and those outliers are geographically interesting. So if we go into data like this is Alison's work, drilling down into different cities. The London one, very much polycentric city. The Liverpool one's interesting. If you look at Liverpool, it's suggesting that there should be a bridge. Okay, a bridge could be expensive, but the fact that you might want to add a bridge there is actually interesting to us, even if we're maybe not costing it correctly. So where we're going with this is we want to do more complex scenarios. So this came from the UK 2070 Commission. So what Alison did here, she's looked at the small changes idea. So the map is showing you different routes. What she's actually doing, she's connecting east-west rail up. Now, there could be reasons why you don't connect east-west rail, because there's an area of outstanding natural beauty in the middle of it. That's probably why they haven't done it. But what she's showing here, if you look at the bottom green line on the graph, the spacing of the stations there matches it. So if you read across horizontally, as you go up, the spacing gets bigger and bigger. So you start at the bottom with 5 kilometre station spacing. Then you've got 10 kilometre, then you've got 20, then you've got 30. And what it's showing is that the high density spacing, the 5 kilometre spacing, you're generating a lot more impact. Now, that's interesting, because that's what we're trying to do. That's what we're saying is, you build a huge HS2 type infrastructure development. I pretty much went up that route today. I should have done HS2 as my map, but it starts in London, it doesn't land again till it gets to Birmingham. What we're saying is you can generate more benefit by breaking that up. And by breaking a big project like that up, you de-risk the project, you reduce the amount of money that the project is going to cost, but you also can generate more benefit overall. It's just people like doing large infrastructure projects. And this is to show you more of the AI stuff. So the idea of generating 1 million data points, which is what we generate from this project, was to firstly train an AI, but also to generate visualizations. So I was looking at what I can give a human planner in terms of a visualization, but also a tool that I can use that is an AI-based tool. So I said there's a problem with this. You can see that the route we were trying to create there was in the middle of where we don't actually have any data. So the 5 kilometre links are all the blue links there. So what we then have to do is create 10 kilometre links and 20 kilometre links, and then connect on a hierarchy. But what Xin actually created here was an interesting tool. So she created a tool where you drop an origin point and a destination point, and you route between those 2 points, and it shows you what the most impactful route is. So you see the green route here is the one that generates the most impact, whereas the blue one is the straight line between the two. And so you can actually do that for any area of the UK that you want. Just go ping, ping, and it just shows you how to route it and generate the most impact. So that's what we actually come up with out of all of this data that we've produced. So to wrap up, building a secure and resilient world. Yeah, network resilience is hard. We can do robustness. We can do that quite easily. Resilience, time to recover from failure, is hard. We've generated 1 million data points on UK infrastructure projects for road, bus and rail. That's open, anybody can use that, so that's what we give away at the end of the project. We've got heuristics for combining small changes into more complex scenarios in a less compute intensive way. And we've got evidence for the fact that this small changes idea actually does work. And with that, I'm going to wrap up.